Hello all, welcome. It is going to be Monday as you are watching this. Hopefully you're watching it on Monday, if not earlier. It is day 2 of section 1.1. When we talked on Thursday, we did the first part of 1.1 where we talked about writing intervals in different ways, in different notations. Now we're going to use writing those intervals. I guess I gotta, oh my goodness. Let's talk about domain and range and behavior in about 10 minutes. So domain and range should be familiar things that you've talked about maybe in Algebra 1. Again, anything in blue, highly recommend that you write down. So domain, get yourself fixed into a thought, a mindset about functions. You remember, like, you input an X, you get out a Y, or you input an X, you get out an f of X, all right? So domain is all of the set of all of the inputs. And if you remember when you started learning about functions oh so long ago, you had a table of values, and we could call it X and we could call it Y. If I input 0, maybe I get out 2. Maybe this function, right? Maybe this function just takes an input and adds 2 to it. So if I input a -4, I'm going to get out a -2. So domain is what we call the set of inputs to a function. In this case, we could call our domain, we have a set of 0 and -4. All right, those are our X values. And that's what I have in the gray. That also might be a good thing you want to write down, all right? So again, domain in a function, there are X values. There's something that we input into a function. On the other hand, we call the range the set of the outputs. So here in this example, my outputs are 2 and -2. Maybe I add, how about 3? This function adds 2, so I would have 5. So looking at this, my outputs would be the set of 2, -2, and 5, right? So again, set of outputs is the range. In our function, we're usually used to saying our range or our outputs are Y values. Sometimes they are called f of X values. As you see in this nice meme, we could use, again, Y to describe outputs, but we really like to use this fancy f of X, all right? Pooh Bear just got a little bit more fancier. This is going to help us distinguish between different functions. So you may have a function name that is f. It does something to x. That's why we call it f of x. And then you get an output of f of x. Again, y and f of x are interchangeable. We like to prefer using the f of x. Sometimes we'll use y if we need to simplify things down. So domain, set of inputs or our x values. The range is the set of outputs or Y values. Take a second, pause if you need to get this down. So again, we're going to start, I guess I wrote on the board. We're going to start using our intervals to describe the domain and range of graphs of our functions. So again, what I said, the domain is all of our X values. This might be a good diagram for you to pause and sketch down in your notes. The domain is all of my X values, so if you think about it, here's my X axis, all right? And then the range, all of my Y values. Again, reminder, here is your Y axis. So let's move on to the next slide. This is a good thing. We could probably come back to it, but I want to get some examples down so you see exactly what I'm talking about. So we're going to be writing those domains and ranges as an interval. Using interval notation is what I like to prefer. All right, here's a function. You don't know what it is. You don't know if it's f of x equals -x squared plus 4. I don't know what it is. But we have a graph of it, all right? We will get into studying specific functions, but right now we're just going to be able to describe a function using the domain and range. So domain, again, is all of our x values. I'm going to add that up here. You may want a sketch of this. Domain is all of our x values. So if we look at this graph, what kind of x values are we using here? Well, if you look at it, I'm going from this point to this point, right? It's kind of contained between here. Is -2 a possible x value? Yeah, my function is defined here. Is -1? Yep, my function is defined at -1 for my x value. Again, I'm kind of looking along my x-axis. Is 0 defined for my function? Yep. So it's looking like all of these numbers between -3 and 2 are going to be defined in my domain. So I'm kind of looking at this portion of the x-axis right here, okay? So if we had to write this as an interval, we'd look at between -3 and 2. Are we including -3 in our domain set? And if you look down, wherever the function is, whenever x equals -3, I see that it is defined. I have an endpoint. It is filled in. So I am including -3 into my domain. And I'm thinking -3 is going to be the smaller number. So I'm going to put a hard bracket on -3, comma. And then I see my function is defined. As I'm moving on my x-axis, it's still defined. I hit that other endpoint at 2, all right? But I'm not including 2 since it's an open circle. So a soft bracket on the 2. So these are ways that we can define our domain. Between -3 and 2, 0.5, right? What are other numbers? -1/4, that's in between -3 and 2. So those are all numbers that you could find on that function. Let's move on to our range. A range, again, our y or our f of x values. So now I want to look at where the function is defined on the y-axis. So here's my y-axis. So, I mean, this may even be easier for you if you take a pencil and you just start to run your pencil up along the y-axis. So here, my function is not defined, it's not defined, it's not defined. I hit that 4 right there. And then all of a sudden, I have my function. It's hitting right there at y equals 4, or f of x equals 4. Okay, and my function is still defined, my function is still defined, my function is still here, it's defined, and then I hit that 5, right? And after this, there's no more function being defined after 5. Okay, so I know that my range runs between 4 and -5. So now I can write that as an interval notation. I know -5 is smaller than 4, so I'm going to write that number first. And I also know that I'm including -5 since I see that endpoint. We're including -5, so a hard bracket on -5, comma, and then I'm going up to 4. All right, and then up there, again, it hits 4, even though there's no endpoint, I know that it hits 4 there, so I can include y equals 4 in there. I'm going to put another hard bracket on the 4 on that edge. Okay, that was a way that we can define our domain and range. Let's go on to the next one. Okay, here's another funny one. Again, domain and range. Let's take a look at our domain, our x values. I'm going to take my pencil here and I'm going to run it along the x-axis, all right? So I'm running it along the x-axis. Maybe here is -8, -7, -6. It's not defined, there's no function. And then I hit x equals -3, right? And there, that's kind of where my function like starts. So I know I'm going to start at -3. It's an open circle, so I'm going to have a soft bracket, comma. Okay, I'm going to start back at -3 and keep going. Okay, it's defined. I still got a function there, it's defined. And then I hit x equals 1, and there's no more function after this, right? So I know my x values stop when I get at 1. So that could be kind of one of your endpoints. And it's going to be a hard bracket because that endpoint, right, where we actually are hitting x equals 1. So I'm going to put a hard bracket on 1. Now let's focus on our range. We're looking at our y values. So again, I think this is a good method. Take your pencil, start here. Okay, no function yet. I haven't hit the function yet. All right, there we go. I hit it right when y equals 0, right on the axis here. So I know it goes from 0, and if I keep going, finally I hit down here at -4, and there's no more function below this. So my y values range between -4 and 0. And I am including -4, so a hard bracket on -4, comma, 0. Even though here I am not including 0, I am here though, right? So I can still put a hard bracket on that 0. Okay, pause if you need to get a sketch of that down. Let's look at a couple more. We're going to go a little faster. So here I've got a function f of x equals -3x. I really hope you can graph a line using slope-intercept form. I have no intercept, so I know I'm starting at 0, 0, the origin. And I have a slope of -3, so down 3 over 1. So here is my function. It is just a line. Now let's describe my domain and range from this. So if I start let's just start over here. We're working ourselves on the x-axis. If I start here, this is where it gets a little tricky, because even though my line does not touch over here, you have to keep in mind that this line is extending forever. So if I had a couple ladders and I could continue this line up the wall, eventually it's going to run into my ruler here, right? So even though I can't see it down here at -10 or -12 or -15, if that line keeps going, eventually it's going to hit my ruler. So if I go to -100, is that line going to hit my ruler? Eventually, right? I mean, it'll take a while. If I keep going up, it'll take a lot of ladders, but -100 is in my domain. So what about as I keep going that way? What about -infinity, right? If I had infinite amount of ladders and I had infinite amount of steps and I could just keep walking that way, eventually my ruler is going to intersect this line. It continues on forever. So what's my smallest number? It's going to be -infinity, right? All right, let's work our other way. We're working this way. What's my largest number? Again, as I get out here, you have to imagine that this line goes on forever. Eventually, I'm going to hit all of the x values, right? So, -infinity to +infinity. That's what we call our real numbers. If you have this equation and you put in any number for x, you can just multiply that number by 3, right? If you put in -3,000 a billion and 1, well, just multiply it by -3. All right? So there is no restrictions on this thing. Your domain is all real numbers. What do you think for the range? Is it going to be all real numbers as well? Yeah, because as you get here, if we start working our way looking on the y-axis, I can just keep moving my ruler up. And if we imagine that line continuing forever, I'm never going to run out of numbers. Same down here. Take your ruler, take your pencil, keep moving it down. If that line truly goes forever, you're never going to run out of numbers. You're going to reach -infinity and +infinity. All right, soft brackets on those infinities because they're not a real number, but they are a concept. Okay, so that was fantastic. Let's move on to the next thing. Let's do one more example. Okay, I'm going to sketch this graph. I have a graph of x squared. If you remember, hopefully from Algebra 1 maybe, x squared looks like a parabola, kind of like that. So let's find the domain and range for this. Domain is all of our x values. So I'm going to start my ruler. I'm going to be working up and down the x-axis. And if I start, again, eventually that arrow is going to reach my ruler. So no matter what x I choose, it's going to keep going off this way. Eventually I'll reach negative infinity or negative 5001. If I go this way, eventually I'm going to reach positive infinity. So am I going to reach, let me put this down. Am I going to reach all of the x values that are possible on that timeline or on the number line? Yes. Again, your domain for this, negative infinity to positive infinity. We're including everything. What about the range? That's a little different. Start your pencil. You could start at the top, you could start at the bottom. If I start it down here, hang on, it's not all real numbers yet because there's no function yet. Still no function, still no function. I hit that y = 0 line, my x-axis, and all of a sudden my function is defined there. So my smallest number that is in my range is going to be y = 0. And am I including it? Yes, I am. Boom, it's right there. There's no open circle. I have to include 0. So a hard bracket on 0, comma. I'm going to keep going. I'm going to keep going. There's still a function. Again, if I get infinite amount of ladders, am I just going to keep going forever? Yeah, it's going up on both sides. Eventually you're going to get there. So my biggest number would be positive infinity. Soft bracket on that infinity. Again, it's not a real number, but it's a concept, all right? Domain and range. Looking at your x values, looking at your y values. I need to set this down because I'm going to poke someone's eye out. Okay, we're doing good. Let's talk about end behavior. End behavior. Here we go. Okay, so end behavior describes what happens to the f of x values as the x values increase without bound or decrease without bound. Wow, that is a lot. Basically, let's kind of pick this apart. What happens to f of x? What's happening to my y values as the x increases without bound? If you increase without bound, you're increasing without a stopping point. You're increasing to positive infinity. So what happens to my f of x or my y values when x goes to positive infinity? And what happens to f of x or my y values when x decreases without bound or when it goes to negative infinity? The way we write this notation is as x goes to positive infinity, all right? That's that first part. As x increases without bound, comma, what's happening to my f of x? F of x goes to blank. That's where you would put your answer, and we'll do that together, all right? I'm gonna move it over just a tad. So that's as x increases without bound, but what about when x decreases without bound? So that would mean that x is, as x approaches, these little arrows kind of mean approaches, as x approaches negative infinity, what's happening to our f of x? And again, that is where you would put your answer. So this is kind of the basic notation for end behavior. In that box, you will usually either put a positive or a negative infinity. Let's get to an example. All right. So here is my first function. It is f of x equals x or y equals x. That's just a basic line. It has a slope of 1. If I had to sketch it out, it's going to look something like that. All right. So, and if you want to imagine, as you're going this way, towards positive infinity on your x-axis. Here is positive infinity. Over here is negative infinity. On your y-axis, you've got negative infinity down here. And you have positive infinity at the top. All right, so let's get to the end behavior. So I'm going to write out that little notation that we had. Let me move it down a little bit. So as x approaches positive infinity, f of x approaches what? Positive or negative infinity. So as x increases without bound, as we travel this way, x is getting bigger and bigger and bigger. We're heading towards positive infinity. What's happening to my y values? What's happening to my graph? I see that as I go this way, my numbers are going up as well, right? We're going up this way towards positive infinity on my y-axis. So as x goes to positive infinity, here our f of x values also go to positive infinity. On the other hand, as x decreases without bound, as we move this way on our this way on our x-axis, we're heading towards negative infinity. What's happening to our function? What's happening to our y values? We're going down as well. So as we decrease on our x, we are also decreasing on our y. Notice how it's going down this way, also towards negative infinity. So the other part, as x approaches negative infinity, f of x also approaches negative infinity. We're decreasing on our x, we're also decreasing on our f of x. Okay, let's do another example. I'm going to leave this notation up here. I'm just going to get rid of the negative infinity, positive, or I should have left that there. I'm going to get rid of this part so we can fill it in for different graphs that we see. Okay. Next one, you actually have the graph here. So, again, if we're looking at this thing, as x approaches positive infinity, I'm just reading from here, as x approaches positive infinity, what's happening to our y values? What's happening to f of x? As we go this way, I see that my function is going down, right? So, as x approaches positive infinity, my f of x's are going down, they're decreasing. So it's kind of switched from last time. All right, the other side, as x approaches negative infinity, as we move this way on our x-axis, our x's are getting smaller. What's happening to our y's? They're getting bigger, right? So as we go this way, my y's are going this way. So as x goes to negative infinity, f of x goes to positive infinity. All right? You're doing good. Hang in there. All right, we got this one here. As x goes to positive infinity, what's happening to my function? As I move this way on the x-axis, I see that my function is going up. So my y's are also going to positive infinity. As I'm moving this way, as I'm decreasing my x, what's happening to my function? Well, eventually, towards the end here, they're going up. So as x goes to negative infinity, f of x goes to positive infinity as well, all right? They're increasing on both sides. Both sides are going to positive infinity. This one's a little bit different. I'm going to move that guy, again, on our x-axis. Negative infinity is this way. All right. Here, we actually have an endpoint on one of these guys. So let's see what happens. So as x goes to positive infinity, as we're going this way, what's happening to our f of x? What's happening to our function? What's happening to my y's? They're going up. So we can fill in that first part. As x goes to positive infinity, f of x also going to positive infinity. And then here, as x goes to negative infinity, this is where it gets tricky. is x actually going to negative infinity? It kind of stops here, right? We have that endpoint. So as x approaches, well, negative 3, it stops here at negative 3. As x approaches negative 3, what's happening to my f of x? Again, we're talking about end behavior, and since this thing kind of ends at negative 3, right? We can't put positive or negative infinity. We just have to put that endpoint. So as x approaches negative 3, what's happening to my y's? What's happening to my f of x's? Well, eventually they stop at negative 3 as well. And again, we can kind of see that in the actual endpoint itself. What is this point on the graph? It's at negative 3, comma, negative 3. All right? So we can describe endpoints, or we can describe end behavior using positive or negative infinities. And if we need to, we can describe endpoints or end behavior using an endpoint in actual numbers. I think that was it. Okay, fantastic. You guys did great. So, I'm clocking in at about 26 minutes. So I'm going to say, I want you to write these graphs down. So 40 minutes. 40 minutes into class. It's kind of a longer section, but I'm glad I broke it up into 2 days. So 40 minutes into class. Come see me, all right? And I will have those instructions. I'm sitting at that meet right now. Come see me, all right? Have a great day. See you in just a second. Oh, I should stop. Stop.